Welcome to the world of deep learning fundamentals. In this introductory video, we will explore the core concepts, architectures, and principles that power neural networks and their wide range of applications in modern artificial intelligence systems. Join us as we unravel the complexities of deep learning and discover how it's shaping the future of technology. Let's begin with the basics of neural networks. Neural networks consist of interconnected nodes, also known as neurons, organized in layers. These connections between neurons have weights that determine the strength and influence of each connection on the network's output. A typical neural network includes an input layer, which receives raw data, hidden layers which process the information, and an output layer, which produces the final result. Additionally, weights and biases are adjustable parameters that the network learns during training. Let's understand how a neuron computes its output. The output y is calculated by applying an activation function, denoted as f, to the sum of weighted inputs plus a bias term. Here x1, x2 up to xn represent the input values, while w1, w2 up to wn are their corresponding weights. The term b represents the bias. In Python, a neuron's output can be represented as shown. The neuron output function takes inputs, weights, and a bias. It calculates z, which is the sum of the product of weights and inputs, and adds the bias. Finally, it returns the result of applying an activation function to z. Now let's explore some common activation functions. First, we have the rectified linear unit, or ReLU, which is the most commonly used activation function. It helps solve the vanishing gradient problem. The formula for ReLU is f of x equals max of 0 and x. Next is the sigmoid function, which squashes values between 0 and 1. It is often used in the output layer for binary classification tasks. The formula for the sigmoid function is f of x equals 1 divided by 1 plus e to the power of negative x. Then there's the tan function, similar to sigmoid, but its outputs range from -1 to 1. It is often used in hidden layers. The formula for the tan function is f of x equals e to the power of x minus e to the power of negative x, all divided by e to the power of x plus e to the power of negative x. Lastly, Softmax is used in the output layer for multi-class classification. It converts outputs to probabilities. The formula for Softmax is f of x sub I equals e to the power of x sub I divided by the sum of e to the power of x sub j. Let's discuss the learning process, starting with the forward pass. In step 1, input processing, data is normalized and fed through the input layer. In step 2, hidden layer computation, each neuron computes a weighted sum and applies an activation function, as shown in the formula h equals f of w, multiplied by x plus b, where h is the hidden layer output, f is the activation function, w is the weights, x is the input, and b is the bias. Finally, in step 3, output generation, the final layer produces a prediction or classification. Now let's move on to backpropagation. Step 1 involves loss calculation, where we measure the difference between the predicted and actual output using a loss function. The formula shown is L equals 1/2 multiplied by the square of the difference between y predicted and y true. Step 2 is gradient computation, where we calculate partial derivatives with respect to the weights. The formula is partial derivative of L with respect to w equals partial derivative of L with respect to y multiplied by the partial derivative of y with respect to w. Finally, step 3 is weight update, where we adjust the weights using the learning rate and gradients. The formula is w equals w minus eta multiplied by the partial derivative of L with respect to w, where eta is the learning rate. Let's explore some common deep learning architectures. First, we have convolutional neural networks, or CNNs, which are specialized for processing grid-like data, particularly images. They use convolution operations to detect features. Key features include convolutional layers for feature extraction, pooling layers for dimensionality reduction, and hierarchical feature learning. CNNs are commonly used in image recognition and computer vision tasks. Next, we have recurrent neural networks or RNNs, which are designed for sequential data processing with memory capabilities. They process input sequences one element at a time. Key features include memory cells for temporal dependencies, LSTM and GRU variants, and bidirectional processing. RNNs are commonly used in natural language processing and time series analysis. Now let's explore some advanced architectures. First up are transformers. These revolutionary architectures use self-attention mechanisms to process sequential data in parallel, enabling better handling of long-range dependencies. Key features include multi-head self-attention, positional encoding, and parallel processing capability. The innovation here is that attention mechanisms allow direct modeling of relationships between all positions in a sequence. Next, we have generative adversarial networks or GANs. These consist of two neural networks competing against each other, a generator creating synthetic data and a discriminator evaluating its authenticity. Key features include adversarial training, a generator network, and a discriminator network. The innovation is that adversarial learning enables the generation of highly realistic synthetic data. Let's discuss some applications and use cases of deep learning. One major application is computer vision, which includes tasks such as image recognition, object detection, facial recognition, medical imaging analysis, and autonomous vehicle perception systems. Common technologies used in computer vision include CNNs, RCNN, and YOLO. Another key application is natural language processing, or NLP, which enables machine translation, sentiment analysis, chatbots, text summarization, and content generation. Technologies commonly used in NLP include transformers, BERT, and GPT. Lastly, deep learning is also applied in time series analysis, which facilitates financial forecasting, weather prediction, anomaly detection, and predictive maintenance in industrial systems. Technologies commonly used in time series analysis include RNNs, LSTM, and GRU. Let's wrap up by discussing future trends and drawing a conclusion. One future trend is resource efficiency, with a focus on developing more efficient architectures that require less computational power and energy while maintaining high performance. Another trend is few-shot learning, with models that can learn from smaller data sets, reducing the need for extensive training data and improving adaptability. Lastly, hybrid architectures are emerging, combining different neural network types to leverage their individual strengths and create more versatile systems. In conclusion, deep learning has revolutionized artificial intelligence by enabling automated feature extraction from raw data, scalable learning capabilities across diverse domains, and continuous innovation in architecture design and optimization. As the field continues to evolve, deep learning remains at the forefront of artificial intelligence advancement, driving innovations across industries and opening new possibilities for solving complex problems. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.